Okay, welcome to our second lesson in exponential functions. This is on transformations of exponential functions. There's two big things that we have to be able to do here. Number one is sketch graphs by identifying and applying transformations. Number two is recognize that an equation of a given exponential can be expressed using different bases. We're going to talk about that. What I'm going to ask you is kind of a combination of both of these. I'm going to ask you to give me the equation of a graph. So the graph will be done. I understand that this is tremendously difficult, and so it will generally be a pretty basic graph. It will have transformations in it, but very, very basic ones. And so the key there is that you can state another equation of the transformation. And so we'll talk about that today. So what you should recall is that transformations apply to all functions, including exponential. And so remember that a and c are your vertical, they're on the outside. K and d are your horizontal, they're on the inside. A and k are multipliers, so they're stretches or compressions. D and c are add, and so they're shifts. And then everything on the inside, remember, is an opposite. So if this was a -2, that would be to the right 2. If this was 2 here for the k, that would be a compression by a half. If that was a half, it would be a stretch by 2. And so remember that if it was times 2, because we want to get to the same base points, we need half as big of x's because we're going to be doubling them. Or if it was a half, we would need double the size of x's because we're going to be dividing them by 2 before we actually perform the function. And so because our inputs are going to change by that much, we're going to do the opposite to get to them. And so the first thing we're going to do is identify and graph the base function. We don't have to graph it every time, but at least show the points, identify the transformations, and then apply those transformations. So b to the x will be the base function for all exponentials. Let's see an example. We've got a base of 3 in the first one, and then we just list out what the transformations are. So the vertical stretch is by a factor of 2, so because there's a 2 on the front. There's a horizontal reflection of a -1. Horizontal reflection, what that does is, like, if we have a 3 to the x graph, a growth graph, horizontal reflection actually makes it become a decay graph. And we know from exponent laws, an exponent law of a negative, what it does is it flips the base. And so instead of a negative, we would actually have instead of a 3 being our base, with the negative exponent, we could use a base of a third. We won't do it that way. Like, you can actually change this graph and use the base points of the 1/3 graph. We're going to do the base 3 with the horizontal reflection. But we'll actually watch for that in the end to actually see that this is going to become an exponential decay graph. And it shifts down 1. Vertical shift down 1. So what we're going to do is, like, we're going to start off with the base points. Sorry, the vertical shift down 1 means that the horizontal asymptote, which was at 0, all the horizontal asymptotes are at 0, it's going to be shifted down 1. So we start with the base graph, which is the 3 to the x graph. And that has these points. So this is the base graph for 3 to the x. Remember that 0, exponent of 0 will give you 1, exponent of 1 will give you a 3. Now that's not of this graph. Like, I don't want to mislead you here. This is just the base graph before it's undergone the transformations. Then I really feel like the best way to do this is to do the vertical stretches and reflections, horizontal stretches, compressions, reflections. Do them to the base points. And so what we'll see is, the graph of the base points is, like, the negative values are actually going to be multiplied by a -1 because there's a horizontal reflection. The x's are multiplied by -1. And the y's are going to be multiplied by 2 because there's a vertical stretch. So just one at a time, we change the x's to negatives. And one at a time, we multiply the y's by 2. Remember that, like, a 9th times 2 is 2 9ths. A third times 2 is 2/3. This 18 point is actually not going to be seen anymore because it's just way off the graph. And so we're going to see something like this. And so this is where we actually get the 1/3 graph. It's going to be an exponential decay graph now that's been stretched by 2. You don't have to do this in the table of values. You can actually do each of these points right on the graph. This 3 is going to be doubled and then horizontally reflected. The 9's doubled, horizontally reflected. The 1's doubled, horizontal reflection doesn't do anything. And so this actually happens right on here. And notice this, the red graph is what our new transformed shape is going to be. We haven't done the shifts yet. So the shifts would actually, each point now from the blue graph, we just shift everyone down 1. And so we'll just finish off by doing the shift down 1. And the horizontal asymptote actually gets shifted down 1 as well. And just let me know which one's the base graph, or the final graph, sorry, f of x. Okay. And so that's your horizontal asymptote at y equals -1. The next one, we've got a base of a half, so we're actually going to use the 1/2 graph. If you wanted to use the 2 graph, you just have to incorporate a horizontal reflection. So that kind of makes things a little bit easier because you don't have to do the base graphs for half or a third. You could just use the base for 2. We've got a vertical reflection from the negative on the outside. And we've got a horizontal stretch by the over 3 is actually incorporating a horizontal stretch by a factor of 3. Horizontal asymptote is at y equals 0 because there is no vertical shift up or down. The base graph is the half graph, so it starts at 0, 1 and then gets halved every time. And I would just use these 5 points, -2, -1, 0, 1, 2. That's what the graph looks like. The x's all get multiplied by 3 because there's a horizontal stretch. Notice that 3x is different than the x over 3 because we have to triple the x's to get back to the same key points. Vertical reflection means that the y values all get multiplied by a negative. And we plot all those points one by one. We get the red graph. Horizontal asymptote still at y equals 0. Okay. There's no shifts in this case, so that is our final graph. And then we just label our horizontal asymptote as well. Okay. What you might want to do, I haven't shown here, is like, because Desmos actually just graphs it, and I just copied and pasted this from Desmos, is just like from this point, actually just do an arrow so that you don't get caught up in wondering where does it go up. And so we just do an arrow on the red line that way and the arrow on the red line that way. So I just put an arrow here, so because if you're not sure where this point is, you don't have to. Like, you just do an arrow to say that it continues to go up. We can see the exponential bend, and eventually it's going to shoot up very fast. So I mean down, shooting down. Last one, we start with a base of 4, vertical compression by a half, and a horizontal shift to the right too. We'll do that horizontal shift to the right after. So the base graph is the 4 to the x graph, so 0, 1, and then multiply by 4 every time. Divide by 4 this way. The y's get multiplied by a half, so a 16th becomes 1 over 32. It's really like hard to estimate, so we're not really sure where it is. So we just put something just off the x-axis. 1 over 16, 1 becomes a half. Like those kind of points I'll really check for. 4, 2, 4 becomes 2, 16 becomes 8. Plot that graph, that's the red graph, and you can see that everything's just is half the size as it was, with the 16 being like something that you couldn't graph originally, but after it's been cut in half, now we can actually see that point. And that's kind of interesting to talk about, because if you didn't do it with the table of values, you still want to make sure that those 5 points are there if they're on the graph. We want to use as many points as we can. Then the last thing we have to do is shift it to the right. And so we just shift it to the right and we get the orange graph. Every point gets shifted to the right too. And so we can see that this point going to here. And we label our graph, and our horizontal asymptote still stays at y equals 0. So here's some practice questions. Try to minimize what the homework was. 5 is really just like a challenge question. Number 6 incorporates that third learning target, and you'll see it on the quiz, but maybe in a little bit different way. And so just if you want to do number 6, there's an example from around, I think, page 247. There's an example for that. For number 3, it doesn't really make sense until you read the question for number 3. There's a reference back to question 1 and 2, and I'm asking you just to do it for number 2. Okay. The big part is the handout, though. Just work through the handout, and that'll be a big part of the homework. Okay.